Okay, thank you, Dr. Benavides. I'm Sean Gilman, and I'm the project manager for Team Ouranos. This is our system validation review for Apophis. So, as an overview, we're going to go over the mission concept, the system definition, the subsystems with their definition, the experimental validation, integration with configuration management, system design, and the system proof of concept, as well as the system validation and conditioning with our programmatics. So, for our project, we divide it into 4 different subsystems, each headed by a technical lead, and then with a integration team, which is headed by our assistant project manager. Our assistant project manager is William Hainsworth. The structure subsystem is headed by Jessica Chow. The command subsystem is headed by Brandon Clefman. The guidance navigation and control, or GNC subsystem, is headed by Abigail Kudo. And finally, the propulsion subsystem is headed by Wesley Stein. So now we'll discuss our mission concept. So Apophis will be a land and air-based system that is capable of carrying a payload of 5 kilograms over a range of 100 meters, and it will also avoid any obstacles in its way in order to reach a target position and deploy that payload. So these are primary system objectives. These are objectives that are mission critical, and anyone that's underlined ones we're focusing on, anyone that isn't are ones that unfortunately due to time constraints we're not focusing on at this time. So begin is that Apophis shall be a land and air-based system, should be able to transport payload with mass that is greater than 5 kilograms, and shall be able to return to the starting position after deploying that payload at the target position. So next is that it should be able to travel more than 50 but less than 100 meters away from the starting position, so it can deploy the payload at the target position. Next is that the platform should have more than one form of propulsion, and then that should have more than one form of attitude control and determination. And finally is that it should be able to complete the mission inside the mission envelope. Now onto the secondary mission objectives. Now these objectives are ones that we expect to complete, and those are that we should be able to avoid any obstacles that are less than 10 meters in width and height. And we'll drive around those or we will fly over them. And then last, we shall be able to keep the platform under altitude of 25 meters throughout the course of the mission. So now the tertiary objectives, which are objectives that are desired to be completed by the end of the mission, and those are that we should complete the mission in full autonomous mode and be fully validated by April 28th. So for our system definition, the structure subsystem holds the platform together. It's where everything is held onto. The command subsystem powers the system, as well as handles all the data relaying between the system and the ground station, and enables manual control of the platform. The guidance, navigation, and control subsystem handles the autonomous function of the platform and controls the guidance of the platform. And the propulsion handles the maneuvering throughout the course using either aerial or terrestrial propulsion. If all this is completed, then Apophis shall be fully operational. Now is a short video of how our system operates. So the system will leave the starting position and continue towards the target position, where it will run into its first obstacle. This obstacle is less than 10 meters in width, so it will just simply drive around it and return to the middle position, and then continue on its way. At this point, it will run into another obstacle. This one is greater than 10 meters, but it will drive in one direction, see if it's less than. Seeing that it's more than 10 meters, it will then drive back to the center position. Once you reach that position, it will then drive 10 meters the other direction, see if that's less than 10 meters. Upon seeing that that's less than 10 meters, it will drive back to the center, at which point it will fly over the obstacle. Once it's over the obstacle, then continue to the target position, where it will deploy the payload. Upon deploying the payload, it will then return to the starting position on the optimal trajectory. These are some of the early concepts that we had. The first was a blimp concept, you can see here. We moved on to a ducted fan and aluminum body system. Then we moved on to something a lot more similar to what we have currently, except that it has a solenoid and tug-aware payload deployment system, as shown here, and a geared front chassis system, as well as under-strut motors. On the current system, we have our aerial motors on top of the struts, as well as a non-geared front chassis system, and an actuated payload deployment system. Now I'll pass it off to William Hainsworth to discuss the system definition.
Thank you, Sean. My name is William Hainsworth, and I'll be discussing the system definition. As you can see here, this is an overview of our CATIA rendering of our project. And we have broken it up into subsystems. So the propulsion subsystem is made up of the 4 aerial motors that you can see on the platform, and the propellers that are associated with that. The terrestrial component is the series of motors and wheels for the terrestrial component. The next portion is the Gnc components. We have separated those into the aerial component, which is using the same motors and propellers to control it in the air, and the terrestrial motors, which will control it on the ground. Also in Gnc, we have a number of systems that allow for figuring out where we're located. Solar arrays on the top, initial measuring unit inside of the circuit system. The obstacle detection system, which is a series of ultrasonic sensors located on all of the aerial struts, several of them facing forward, several of them facing out to the sides, and one in the back that faces down to tell us whether we are on the ground or we've cleared an obstacle. The command subsystem has a series of batteries, electronic speed control units that control the aerial components, the microcontroller and sensors which communicate with the ground station and the transceiver. Our structure is the final component that holds everything together. This is a series of plates, struts, stringers, battery cage, and a chassis for the forward and aft. And then the payload system, which is located on the underside. Also over there is the payload itself. System concept, final wireframe drawing, final implementation. I'd like to now turn this over to Jessica Chow to discuss the structure subsystem.
Thank you, William. Again, my name is Jessica Chow, and I'm the Structure Subsystem Lead. With me on my team is Corinne Rodabaugh. So first, the Structure Subsystem definition. As Jeff previously stated, structures is the component that holds the rest of the system together. Our components include the carbon fiber aerial struts, the carbon fiber plate, the aluminum stringers that are underneath each aerial strut, and then also the forward and back chassis. So there are 4 requirements within the structure subsystem. The first is that we shall support a mass that is less than 18 kilograms, support a thrust that is less than 27 kilograms force, support a torque that is less than 2.6 Newton meters, and also that we shall deploy a payload with a mass that is greater than 5 kilograms. As you can see at this table, we have each requirement and the design metric used to validate them, and also our methods of numerical and experimental validation. So in order to numerically validate all of our structures requirements, we use CATIA and also CATIA finite element analysis. And in a few moments, I will go over the methods of experimental validation. Again, here's the software we used, CATIA and CATIA finite element analysis, and the following assumptions that were made. We assumed most of the material properties that went into our components or structures, including factors of safety, mostly within the density in order to get an upper bound on how much our structure would weigh. We also assumed that our carbon fiber is an isotropic material, which it is not, but that is the only form of finite element analysis available within CATIA. So here for our first test was our platform mass test. This was to verify that the overall mass had a system mass that was less than 18 kilograms. In order to perform this test, we took our full system and weighed it using the foam in order to balance it out to fit on the scale. Our second test was our thrust support test, which would verify that each strut and the plate could support a thrust of 6.75 kilograms force. In order to perform this, we took the structural components of the plate of our system, flipped it upside down, and hung weights in order to mimic lift. So we used all the structural components, which are the carbon fiber and the aluminum, and also a series of stringers and weights. Our third test was our torque test, which would verify that the overall system could support torque from our ground motors. In order to perform this, we assembled the full system and drove it on the sidewalk down to the lower fields. And our fourth and final test was our payload mass test, verifying that our payload had a mass that was greater than 5 kilograms. To verify this, we weighed our payload. And now I'd like to pass it off to Corinne Rodabaugh, who will go over our structure subsystem validation.
Thank you, Jessica. Once again, I'm Corinne Rodabaugh, and I will be doing the structure subsystem validation. First off is the mass of the platform. We weighed it on a scale. Our CATIA platform mass shown by our model was 17.567, while the scale shows 17.06. This difference, once again, is from overestimating the densities in our CATIA model to ensure we had a bit larger cushion when we actually built our system. Next is that it survived both the torque and the thrust of our system when it was operational. We did this by checking for delamination, cracking, and plastic deformation in all of our structural pieces. As you can see, it survived testing and did not have any of those breaking or cracking. Last, we weighed the payload. with a actual payload mass of 5.026. This is the weight of the actual weights, not the plate that it sits on. As you can see, we numerically and experimentally validated all of the requirements for the structure subsystem. Some improvements, though, that we could have made, particularly is material properties, specifically for the exact layup of carbon fiber we are using, as in how much it bends and when exactly it would break. Now I'd like to bring up Brandon Kluffman for the command subsystem.
Thank you, Corinne. Hello, everyone. My name is Brandon Kluffman, and I'll be discussing the command subsystem. On my team with me is also Estelle Fortes. First, I'll start off with the command subsystem definition. The command subsystem is made up of major components. Primarily, we have the 4 lithium polymer batteries, which are located here. These are 6-cell, which they're 22.2 volt batteries. We also have our microcontroller and sensor unit located here on the front of the platform. ESCs for the, electronic speed controllers, or ESCs, for the 4 aerial motors are located on the 4 struts. And then we have our transceiver, which communicates with our ground station located here. And then lastly, we have 2 custom printed circuit boards, which power our ground motors. Those are located actually inside the solar panel box. You can't see them at the moment. We also made a Windows program for our ground station. As you can see here and here, this is the information that we sent from the platform to the ground station. This gives you information such as the acceleration, gyroscope, magnetometer, and latitude and longitude of the vehicle in real time. In addition, you can connect a controller, such as an Xbox One controller, to the ground station in order to manually operate the platform. It allows you to operate in both ground and aerial mode by switching between the modes. Lastly, if you don't want to operate with the Xbox controller, you can actually command a target position by inputting a latitude and longitude and clicking send, at which point that the vehicle will proceed to go to that target position. For the requirements of the command subsystem, the first is that the communication range between the ground station and the command subsystem should be less than or equal to 200 meters, and the update rate between those should be greater than or equal to 1 hertz. The third requirement states that the command subsystem should have more than 50 interface pins to communicate with sensors and actuators. Fourth, fifth, and sixth requirements deal with our battery that we selected. The nominal voltage should be greater than the nominal voltage should be 22.2 volts. It should have a greater than 261 amp hour current supply and should have more than 16 amp hours of battery capacity. In the far column is the requirement. The next column is the design metric we use to validate these requirements, our numerical method for validation, and lastly our experimental test that we perform for the validation of these requirements. All of our requirements, except for the first one, use the specification of the actual components that we selected. The first requirement, however, was a MATLAB software that we use to perform calculations for our digital signal-to-noise ratio for our communication system. Requirements 5 and 6, once again, this is for our battery. We use the specifications of the batteries that we selected to validate these requirements numerically. The assumptions we made when we performed our MATLAB calculation was basically to determine the digital signal-to-noise ratio. We assumed that we had a perfect medium and there was no interference with the communication system. We performed a total of 4 tests for our command subsystem validation. The first test was our communication range test. The purpose of this test was to verify that our radio worked up to 200 meters and had an update frequency greater than 1 hertz. As you can see here, the ground station was positioned with our first technician at that location. The second technician proceeded to walk with the microcontroller unit using a track and field measuring tape out to the target position. During the test, the technician at the ground station monitored the update rate of the ground station and recorded that value. The next test we performed was the battery voltage test. Upon receiving the batteries, the first thing we did was balance and fully charge these batteries. It should be noted we're looking for a nominal voltage of 22.2 volts. Within the battery industry, for a lithium polymer battery, that's referred to as the resting voltage. The actual fully charged battery voltage will be about 25.2 volts for this particular battery, and the lowest acceptable safe battery voltage will be 18 volts. For this test, we strictly connected a voltmeter up to each of the 4 batteries and verified that their voltage was indeed 25.2 volts or about. The next test we performed was the instantaneous current test. The goal for this test was to verify that each of our batteries could provide more than 65.25 amps each. To perform this test, we connected a single battery to 2 of our aerial motors in parallel, thus maximizing the current draw for the system. We used an amp clamp located here to measure the actual current running through the battery. And the goal, again, was to verify that we got enough current for each of the 4 batteries. Our last test that we performed was the battery capacity test. For this test, we connected this ammeter in series with one battery and 1 aerial propeller. The goal of this was to verify that we could constantly drain the battery at a known rate. For this test, we ran it at 9 amps. That was about the limit of our ammeter that we used. We ran this test for 27 minutes to calculate a total of 4 amp hours of battery capacity drained from the battery. At this time, I'd like to pass it off to Estelle Fortes to discuss the command subsystem validation.
Thank you, Brendan. I'm Estelle Fortes, and I'll be discussing the command subsystem validation. The first test we conducted was a communication range test. This test validated our first subsystem requirement. The expected range as determined by the specifications of our radio was 0 to 1,000 meters. We experimentally verified a range of 0 to 204.5 meters, therefore experimentally validating this requirement. Furthermore, in the communication range test, we were also able to validate our second subsystem requirement. For this requirement, the desired bit rate was 672 bits per second. We experimentally measured a bit rate of 1,350 bits per second, which equates to an update frequency of approximately 2 Hertz, therefore experimentally validating this requirement. Next was the microcontroller verification. This verification validated our third subsystem requirement. For this requirement, the desired number of pins on the microcontroller was 50. We simply counted the number of pins on the microcontroller, which was 80. Therefore, we were able to experimentally validate this requirement. The third test we conducted was a battery voltage test. This test validated our fourth subsystem requirement. This test was conducted for each battery. Each battery was balanced, charged, and then we measured the voltage across the battery using a voltmeter. Fully charged, each battery had a voltage of 25.1 volts, therefore validating this requirement. The fourth test we conducted was the battery current test. This test validated our fifth subsystem requirement. For this requirement, the desired current draw from each battery was 65.25 amps. We tested each battery to a current draw of 70 amps. Collectively, all 4 batteries produced a total current draw of 280 amps, therefore experimentally validating this requirement. Here's a short video clip of the battery current test. Seen at the top and right are the 2 aerial motors connected in parallel to our battery seen here. At the bottom is the amp clamp in which we use to visually monitor the current draw throughout the test. The fifth and final test of the command subsystem was the battery capacity test. This test validated our sixth subsystem requirement. Again, this test was performed on each battery. After this test, we measured the voltage across each battery. Because these voltages were greater than the minimum safe voltage of 18 volts, we were able to prove that each battery had capacity remaining. Here's a video of the battery capacity test. Shown at the top is the single aerial motor connected in series with the battery, and down here is the emitter. In summary, the command subsystem was able to both numerically and experimentally validate all 6 of our subsystem requirements. At this time, I'd like to introduce Abigail Kudo to discuss the guidance, navigation, and control subsystem.
Thanks, Estelle. Good afternoon. My name is Abigail Kudo, and I'll begin by introducing the guidance, navigation, and control, or GNC subsystem. Joining me on GNC are Damian Barraza and Christopher Klein. I'll begin with the subsystem definition. The primary method of attitude determination for the platform is the inertial measurement unit, which is located on a booster pack on the microcontroller. The secondary method of attitude determination is the directional sound sensor, located on the top of the platform. The airbase controller uses the 4 motors and propellers on each of the struts to adjust the attitude of the platform during flight, and the ground-based controller uses 2 motors independently driving the 2 wheels for speed differential steering and front-wheel drive during ground travel. In autonomous mode, the guidance component is responsible for detecting obstacles using the obstacle detection sensors and for navigating the platform to the specified position using the position sensor located on the top of the platform. The requirements for the GNC subsystem are shown above. The first 2 requirements state that GNC shall have more than one method of attitude determination and attitude control. The third requirement states that GNC shall navigate the platform to a point that is less than 2.75 meters from a specified position. Requirements 4 and 5 state that GNC shall navigate the platform around translational obstacles that are less than 10 meters in either length or height during the mission. Requirement 6 states that GNC shall limit the altitude to be less than 25 meters during the mission. And the last requirement states that GNC shall complete the mission using less than 16 amp hours of battery capacity. The following table shows the first 3 subsystem requirements, as well as the design metric used to validate these requirements, the method of numeric validation used, and the methods of experimental validation used. Note that for requirements 1 through 3, we either use specifications or a simulation to numerically validate these requirements. Here's a similar table for requirements 4 through 7. Note their design metrics and that all of these requirements were numerically validated through simulation. Unfortunately, due to time constraints, we were not able to perform any of these tests, therefore not experimentally validating requirements 4 through 7. For the first method of numerical validation, we use the manufacturer specifications for 2 elements to numerically validate requirements 1 and 3. The second method of numerical validation we used was a simulation in Simulink. Here's a simplified top-level diagram of our ground control simulation containing a control law and a plant. The plant featured a model of system dynamics, which included some simulated disturbances, and the control law featured a PD controller to adjust the position and heading angle of the platform during ground travel. The assumptions made during the simulation are listed here. Most notably, we were not able to model the caster wheel dynamics of the platform. We did a similar simulation for the air controller. Again, this is a top-level diagram in Simulink containing the control law and the plant. The plant featured a model of system dynamics. Fortunately for the air-based controller, we were able to simulate the motors and propellers as a first-order system, therefore eliminating that instantaneous acceleration assumption. The control law featured another PD controller to adjust position and attitude during flight. The assumptions that we made during the simulation are listed here. Most notably, we did not account for any structural vibration of the platform during flight. We did, however, account for the bending of the struts due to the thrust applied at the end of these struts during flight. In summary, the simulations together numerically validate these GNC subsystem requirements 2, 3, and 7, and independently, they numerically validate requirement 4, 5, and 6. Moving on to our methods of experimental validation. The first test we performed was to experimentally validate our primary method of attitude determination. For this, we used the 3-axis rotation table located in the Space Systems Lab. First we performed a calibration on the gyroscopes and the accelerometers of the IMU. We accounted for any bias, misalignment, or scale factor that may have occurred in the gyros and the accelerometers. After we performed the calibration, we conducted a validation test where we programmed the table to go through a series of roll and pitch angles. We compared the measured roll or pitch angle from the IMU to those desired angles. That difference had to be less than 0.5 degrees to experimentally validate the requirement. We performed this test on 3 separate sensor booster packs, hoping that one of those would experimentally validate the requirement. The next test we performed was to experimentally validate our method of ground control. For this test, we conducted it on the sidewalk by the lower fields. We used the full system assembled. The user manually commanded the platform to turn 90 degrees, and we were able to verify that the platform did indeed turn 90 degrees. If it did, we were able to experimentally validate the ground controller. The last test we performed was also conducted on the sidewalk by the lower fields. This was to validate the positional accuracy requirement. We started at this location here, manually drove the platform first 10 meters, then 30, 60, and 100 meters. At each of these points, we measured the distance between the platform and the specified point. That distance had to be less than 2.75 meters to experimentally validate this requirement. Now I'd like to introduce Damien Barraza to discuss the validation of the GNC subsystem.
Thank you, Abigail. Again, my name is Damien Barraza. I'll be going over the GNC subsystem validation. For the first requirement, we consider 2 methods of attitude determination where we use a design metric of angular measurement accuracy for both these methods. For the first method, we use the specifications from our inertial measurement unit, or IMU, to obtain a simulated angular measurement accuracy of at most plus or minus 0.005 degrees, and experimental angular measurement accuracy from the actual hardware to obtain at most plus or minus 2 degrees. Since we were not able to validate the first method, we were not able to begin testing for the second method. That's not validating that method as well. So here, from booster pack 1 here yielded the best results for roll, where we can see here that our measured angles were not within 0.5 degrees of our desired angles. Again, booster pack 1 also yielded the best results for pitch, where we see once again that our measured angles were not within 0.5 degrees of our desired angle. For the second requirement, we consider 2 methods of attitude control. Where for the first method, the ground controller, we considered that metric of turning ability, where we simulated a turn of 90 degrees autonomously and experimentally manually controlled the platform to turn 90 degrees as well. Since we were not able to test the second method, an air-based controller, we were not able to validate this requirement. So here is our simulated 90-degree autonomous control. As you can see, we achieved 90 degrees. And here's our experimental manually controlled autonomous experiment, which by visual inspection was achieved. For our third requirement, we consider design accuracy of positional accuracy, where we use a full system to test our ground controller. Here we simulated the platform grabbing to autonomously to specified positions and manually control the platform to specified positions as well. So here is a short clip of us driving to the specified point of black tape, where we measured the specified position and the distance from that point to the center of the platform, which in this case was less than 2.75 meters. So here is the results for the Gnc subsystem validation, where we were unable to validate numerically and experimentally requirement number 1. We were able to validate requirement number 2 numerically, but not experimentally, since only one method was validated correctly. And requirement number 3 was validated numerically and experimentally. As for requirements 4 through 7, we were able to validate all these requirements numerically, but not experimentally, since we were not able to conduct these tests. So here are some future improvements. The biggest one that we took from this was the first one. In the future, we would rewrite the requirements not only more clearly, I guess, but instead we would separate the manual and autonomous modes. That way, when we do future testing, this would eliminates or mitigates the ambiguity of validating these tests during experimental testing. And now to Wesley Stein for the propulsion subsystem.
Thank you, Damien. I will be discussing the propulsion subsystem. Joining me on the propulsion team is Eli Olson. Now, our propulsion subsystem consists of the 4 aerial motors with their propellers, the 2 powered front wheels with their 2 motors, and the 2 unpowered rear caster wheels. Now, our requirements for the propulsion subsystem: it shall transport the platform with the payload over a distance that is greater than 50 meters and less than 100 meters from the starting position. It should be capable of translating the platform more than 10 meters from its current course to avoid an obstacle. Prevent the platform from ever exceeding an altitude of 25 meters during the course of the mission. Provide 27 kilograms force of vertical thrust to lift the platform. Be capable of providing a maximum torque to the drive wheels greater than 0.11195 Newton meters, and transport the platform without the payload over a distance less than 100 meters to return to the ground station from the target position, and have more than one form of independent propulsion. Now, the 2 independent forms are aerial and terrestrial. Now, the means in which these requirements were validated was manual driving for the range requirements, including the obstacle avoidance. For maximum altitude, we planned on manual flight. For thrust, a test was conducted with a string beam. For torque, a torque bar test was conducted. For the movement with no payload, also manual driving. And the number of methods is simply count them, aerial plus terrestrial. Now, I will briefly discuss the assumptions we made in numerical validation and our methods. We used Simulink and MATLAB to perform our numerical simulations. We assumed for the motors, we used brushless motors, so the descriptive equation gives RPM as a linear function of voltage. We assumed no inefficiency in the motors and instantaneous response. Furthermore, for the propellers, we assumed an equation in which the thrust is proportional to the square of the revolutions per minute in a quadratic relation. Since these were designed for use at sea level, we assumed a linear reduction in thrust with the reduced air pressure at this altitude. And we also assumed that we could use polynomial interpolation in between the RPMs at which the thrust coefficient was specified by the manufacturer. Now, the first test with the torque bar was conducted in the senior design lab and consisted of using a cantilever torque bar on the motors with a weight at the end to measure the total torque output and verify that it could produce the desired 0.1195 Newton meters. The second test with thrust was conducted in AXFAB and was performed on all 4 motor propeller combinations with their 4 batteries, therefore using the same power source we would later place on the platform. The purpose was to verify that each of these could produce the required thrust to reach 27 kilograms force in all. Now, this is a diagram showing the setup. Now, as you can see, the motor is placed at the end of a cantilever beam. There is a strain gauge on the beam, and the strain is linearly proportional to the thrust. Thus, we would place the entire apparatus behind blast shields to protect against an accident, and then increase the motor voltage and speed until we reached our maximum RPM, which was 8,000, measuring all the time the thrust produced by means of the strain gauge, in that the strain of the cantilever beam was linearly proportional to the thrust. I will now turn the time over to Eli Olson, who will be discussing the validation of this subsystem and the results of these tests.
All right, thank you, Wesley. I'm Eli Olson, and I'll be discussing the validation of the propulsion subsystem. So for our first test, we had our torque test. We got significantly less torque than was expected based on the manufacturer data, but it was still easily enough to validate our requirement, meaning this requirement was well validated experimentally. For our thrust test, our 27 kilograms force was based off of the goal of having a 1.5 thrust to weight ratio for our platform. But since our weight was less than what was originally predicted, we have a design thrust to weight and actual thrust to weight listed. In either case, however, we were unable to meet the requirement or the intent behind the requirement, meaning the thrust was not validated. Here we have a short video clip from one of the thrust tests in progress. This was when we had an aluminum beam for measuring the strain. You can see there was a lot of deformation there, some of which became permanent, causing a offset in the data. For later tests, we use a steel beam to prevent this problem. Here's data from one of the tests with the steel. Well, we were manually throttling up our propeller throughout this, and the red line represents the level of thrust we would need in order to validate our requirement. As you can see, we got close, but did not validate the requirement. For our last test we were able to perform, it was the number of methods of propulsion. As mentioned, we have aerial and terrestrial propulsion, giving us more than one form of propulsion, validating said requirement. Here is a summary of all of our requirements. Due to hardware failures, we were unable to test most of them through a driving test, and the ones discussed before were either validated or not validated. All were numerically validated beforehand. So potential improvements for the system. We could implement a low-pass filter into our data acquisition to remove the significant amounts of noise we saw during some of our tests. And we could work on reducing the sources of error in our predictions, such as inefficiencies. We did not account for the inefficiency of the propeller. In a brushless motor like this, that would typically be around a 98% efficiency, which would explain some of the getting close to but not meeting our requirements we saw. I will now pass the presentation to Joseph Prosper to discuss the integration.
Thank you, Eli. My name is Joseph Prosper, and I will be discussing the integration team. On the integration team, we have William Hainsworth, who is the assistant project manager, myself, and Kalen Hubner. And now I'll be going over the configuration management and how it works. So for each document that we have, there are 3 numbers that are associated with the document. The first 3 numbers is the family number, the next 4, the instance number, and the final 2 are the flavor. So for this piece in particular, the ultrasonic bracket right, the family is 047, the instance is 0203, and the flavor is 01. So to get a little bit into more detail with that, the first 3 numbers, the family identifier. So as you can see up here, the 047 is fabricated sheet metal parts, which is what that was. If you look at among this list, some notable ones are 065, which is the product structure tree, the 200, which is the subassembly bill of materials, and 300, which is the subassembly drawings. To get into the instance, here is an example. We have the 300 subassembly drawings. This is every single subassembly we have on Apophis. And if you notice, the aerial subassembly and the propeller subassembly has X's at the end. This is for the flavor. Moving on to the flavors, this one in particular, the propeller strut, 9990097. For the front strut, which is the basic one, it's a 44 length propeller strut with 2 holes at the end. That is the basic one. For the second flavor, the sides, the 01 designation, it is slightly shorter. It is 42 centimeters as opposed to 44. And for the rear, it's the same length, but we have 4 holes at the end for the ultrasonic sensor instead of the ultrasonic sensor bracket. Here is our product structure tree. You can see how everything is arranged on here. We have, for example, we have the body, and connected on the body, we have the 4 aerial struts plus the bays, and connected to the 4 aerial struts are the different propeller subassemblies. Here's a sample of one of our bill of materials for the front wheel subassembly. You can see the part numbers listed here, and the description of what those parts actually are, and how many of each of those parts go on this particular subassembly. Here's an example of one of our subassembly drawings. This is, once again, for the front wheel subassembly. The first page shows the completed subassembly, and then each subsequent page shows how you create this subassembly in particular. So for the first step, you insert the wheel bearing into the front chassis, then you attach the axle to the motor, attach the motor to the front chassis, and then finally attach the wheel to the axle. And finally, here is an example of one of our part drawings. Each part drawing has everything you need to create this part, any sort of measurements and any sort of angles on this part. So in total, it is a 4-level product structure tree with 15 different unique subassemblies, 25 subassemblies in total, 105 unique parts with 15 flavors, with a total number of 763 total parts. This is the status of all the documents. All the documents have been assigned document numbers, and all of the documents have been released to the customer, and with all of those documents are hyperlinked together. And now I'd like to pass it off to Kaylin Huebner and talk about the system design requirements.
Thank you, Joseph. Once again, I am Kaylin Huebner, and I'll be first discussing the system design requirements. So the platform should be able to deliver and deploy a payload that is greater than 5 kilograms. It shall transport that payload a distance that is greater than 50 meters but less than 100 meters from the starting position. It shall deliver that payload to a position that is no further than 2.75 meters away from the target position. And then it shall travel a distance that is less than 100 meters from the target position back to the starting position without the payload. The platform shall maintain an altitude that is less than 25 meters during the course of the mission. The platform shall have more than one form of propulsion, more than one method of attitude determination and control. The platform shall not upright if the amount of precipitation for the current day is greater than 0 inches. It shall travel around obstacles that are less than 10 meters in the horizontal and vertical direction when the platform initially detects that obstacle. And lastly, the platform shall have a total mass, including the payload, that is less than 18 kilograms. For the system proof of concept, none of our requirements were actually validated because when we tested Apophis, it was not in the full integrated system, but we do have some tests to prove concept. Our first is our payload deployment system. As you can see, our solar panel box is not on the platform and our aero motors are not hooked up. For our last test was a full throttle test. This was a proof of concept that all 4 motors would work together. This was performed in the Space Systems Lab in AXFAB. So how we performed this test was an iron plate was strapped down to the front and the rear propeller struts of Apophis, which was placed on 60 kilogram capacity scale. We had 3 tables surrounding Apophis with two blast shields for a safety barrier. A USB connected the electronics on Apophis to the ground station, which is located behind the blast shields. And lastly, 2 ratchet straps were placed over Apophis to provide stability. So I'd like to show a video now. The maximum thrust that we actually calculated from this test was 23 kilograms. And lastly, for our conclusions, due to time constraints, power malfunctions, and manufacturing limitations, none of our system requirements were validated.
For improvements, firstly, design complications cause unforeseen effects from our system after redesign. For example, our servos did not work well with our electronics, so next time during redesign, we would like to take more time to make sure everything is compatible so no unforeseen effects occur. And secondly, system simulation should have been varied more for a wider range of mission envelopes. For example, Apophis should have been simulated to drive on grass, coarse gravel, and concrete. Now I'd like to pass it off to William Hainsworth to talk about system validation.
Thank you, Caitlin. My name is William Hainsworth, and I'll be discussing the system validation. So as discussed, because of the problems with the time constraints and construction, we had all of our primary system objectives, the associated system requirements, and whether or not we were able to actually experimentally validate any of them. We were not able to test those. So the next 3 slides are just talking about the primary system objectives, the associated system requirements, and the experimentally validated or not. This is the secondary system objectives, whether or not the associated requirements and testing. And then our final, the tertiary system objectives, associated requirements, and whether it was tested. So we were not able to test and validate the system as a whole unit. We were able to test separate subsystems. I'd like now to turn this over to Sean Gilman to discuss the programmatics.
Thank you, Jeff. Now we'll discuss programmatics. So I can see as to date, we've done 5,321 hours worth of work through both semesters. For our project budget for initial allocation of $2,000, we spent all but $224.33. These are some of the lessons learned. These are some more. We'd like to highlight that I'd like to accept that there will be delays in the project, and that healthy team dynamics allow for a more productive team. Now for the summary. So in summary, we've gone on mission concept, the system definition, subsystems with their definition and experimental validation, integration with configuration management, system design, and system proof of concept, and then system validation, and finishing off with programmatics. We'd like to acknowledge the people, especially Dr. B and Dr. McElwain, for helping out Team Ouranos during the course of our project. Now I'd like to thank our panelists, ask my team to join me up here and open the floor for questions.
And we have about 15 minutes for Q&A.
This is Greg Bunting, Sandia National Labs. So I had a few questions on your design that I'm not sure that you touched on. So wheels, I'm just curious, I guess what's the decision process behind what they ended up as? So.
I can defer to Leslie Stein.
Thank you. The wheels, front wheels are powered, rear wheels are not. When designing the front wheels, we had to deal with 3 different design considerations. First, that they had to be able to obviously move the platform as powered wheels. Second, they had to be strong enough to withstand landing on them, because they must function as landing gear in addition to a propulsion system. And third, they had to be light enough not to burden the platform during flight. And this is what led us to come to this machine from solid aluminum with lightning holes and these windows, as you can see in the edge of the wheel, attached by steel pins and bolts inside to the axle. And so these were the most complicated in-house part that was manufactured. And the rear wheels are casters. Originally, we considered making rear wheels that were identical to these and then putting them on mounts, also to be unpowered though. But we abandoned that simply due to the complexity of designing a swivelable mount with this wheel on it. It was simply beyond the resources we had, so we went with casters that we could mount.
Okay. So I had a question. You were testing your sensors, and you mentioned that the IMU failed the test to determine where it was, and therefore you couldn't test the solar sensor. And so I'm a little confused about that. Why did one failing mean you couldn't test the other one?
I will defer to Abigail Kudo.
So yes, our primary method of attitude determination was the IMU. That was easy enough to calibrate and validate indoors because we could do it on the rotation table. Our secondary method, we chose the sun sensor. We couldn't simply put that on the rotation table because it was indoors, so we needed to test it outside. The method to validate that, the way we were going to validate that method was by using the primary method. So assuming that the primary method met the accuracy requirement, that would then be considered truth. And then when we perform the validation of the secondary method, we'd be using the IMU as the true value of attitude.
Can you think of a way that you might be able to measure it without the IMU data?
Yeah, so halfway through the semester, after we figured out that the rotation table had some issues with the way we were conducting the validation test, it was brought up to us that we could have simply taken a steel sheet, put it at an incline, put a digital level with an accuracy of 0.1 degrees, which is less than that requirement, and validate it that way. Again, at that point, we had already done the 3-axis rotation table test on 3 booster packs to try to validate the requirement, and it was halfway through the semester. We were spending way too much time trying to do that, and it was hanging us up, and we weren't able to move forward. So we were just simply out of time at that point. But eventually, yes, we did come up with a better way to validate it.
Okay, thank you. So I was going to say that I really liked all the structural testing you did on your parts where you put the loads on them to see how they would do it and to kind of experimentally verify that way. So one question was when you tested the thrust of your propellers, you took a cantilever beam and put strain gauges on it to measure the thrust. And I was just curious as to how you came up with that and what kind of repeatability you got from that experiment. And once again, if you could think of maybe a better way or a different way to do that might be more reliable.
Defer to Eli Olson.
All right, so we did consider a couple of options with other things. We chose the cantilever beam and strain gauge because it would be one of the simplest options to put together. And other than the problem we got with the aluminum beams where we got the permanent deformation, then we got fairly consistent results through the tests of a strong correlation line fit between the force exerted and the strain measured. So we're pretty happy with how those turned out. Does that answer your question?
Yeah, I just pictured, just a spring scale, like a linear spring scale that you pull on and it gives you force.
So we did discuss doing that. One of the problems we considered, that's why we didn't do that, was the possibility of downwash from the propeller affecting the measurement. And then because of the propellers going as fast as they are, then it would need to be a spring scale that our hands wouldn't be anywhere near because we like our fingers. So is that?
Yeah, thank you. And then I guess a question for, the team lead is what would you have done differently now that the semester's over? Well, one, if you had another month, and two is, from the beginning, knowing what you know now, what would you have done differently?
Well, we would have never gone with the geared front chassis system, I'll tell you that. But we would have simplified a lot of it because we ended up making 5, 6 redesigns. And yeah, if we had an extra month though, we'd definitely rework the electronics because that was really what prevented us from doing a lot of our mission tests. Get that done, and then we could potentially fly.
Yeah, and then, another observation was you spent, some amount of time on sensors and seemed like you never even got to the stage where you could try an autonomous mode. So,
Yeah.
So what's the value in sensors until you get the manual working, I guess?
We worked on the sensors mostly last semester when we still were planning on doing an autonomous run. They're only really useful for that. So once we got into this semester and we started having all the redesigns and the flight controller didn't start working, and that was in the same group of people that did the sensor work, we decided to put that on the back burner so we could at least try and get the flight controller done. So that kind of put on the wayside.
Okay, thank you. And it was good work, and maybe if you had more time, you'd be able to have a cool demonstration.
All right, first and foremost, thank you all. That was very amazing. Not gonna lie, I was a little intimidated when I walked in and I saw that. Anyways, my name's Scott. I'm from Raytheon Missile Systems, and I'm here to hopefully help you guys. And one of my first questions is, why did you guys choose carbon fiber? did you perform any sort of trade study, or what was the choice?
Okay, I'll defer to Jessica Chow.
It was free. Actually, we have a large freezer full of carbon fiber that Boeing Mesa donates to us. We did do some testing at the beginning of prelim onto different layups as to how many layers we would need using the specimens provided by Dr. Lanning, and it was determined that carbon fiber was suitable, but actually turns out, as we later learned, the carbon fiber that was available in the freezer was not the same carbon fiber that we had been testing with, so we ended up making modifications to our layup later this year, or this semester.
Okay, gotcha. So then, one of the things I noticed was missing, and not to compare you to the previous group, but they had requirements for temperature, and I noticed there was nothing. So what sort of operating conditions are bounding your design? Sort of weather.
I'll pass out to Brandon Clefman.
So to go back to the previous presentation, that was actually a requirement given by the customer, but which was not given by us.
Okay.
So we had no regulation as far as temperature or weather conditions. However, we did add in a mission envelope, you could say, so we didn't want to operate in rainy weather, for example, because obviously you look at the electronics, it's not protected at all. It was a little too much for us to do, I would say. It would have been something that we could do for, say, a finished product for sure, but for this, it was probably a little too much for us to do. That's what I would say.
Well, that's fair. I was just curious. One of the other things that I noticed, and I was actually kind of curious on, did you guys sort of test or decide to test at all what your maximum rate of descent would be when landing? And the reason I ask is because that also affects what your structure looks like.
So we did have a maximum rate of descent, but that was in the component level requirements. So on the system level, we did not have a requirement that specifically relates to descent speed. I believe we capped it at 0.5 meter a second max descent speed.
Okay, is that something was that shown in your presentation?
No, that was under the component level for propulsion. Okay. So it would have been under the aerial component.
Okay. So one of my other questions. Oh right, yeah. So you guys mentioned you didn't analyze structural vibrations, and that's perfectly okay. It's an undergraduate course, and there's no expectations there. But that being said, when it comes to your IMU, your accelerometer data, is there correction for or concern for vibration, and how you would account for that? I mean, I know you guys didn't get that far, but just curious if you thought about it.
Pass on to Brandon Clefman.
So for the actual hardware that we purchased, it actually has a built-in filter that helped with that. I don't know if it pertained exactly to the frequency we were seeing in our structural vibration. Again, we didn't get to test that, so we don't know what the frequency was. We did actually, when you were watching that full-throttle test video, you could clearly see that the structure was vibrating. The struts were vibrating all over the place, and at certain spots, at certain throttles, you would actually get a natural frequency within the carbon fiber, and it would start to kind of oscillate, which was kind of cool to see. We didn't get to test that. The IMU that we did have a hardware filter though, but we did not implement a software filter. We had plans in our simulation to do it, but we found that it didn't actually help very much, so we put it kind of on the back burner, you could say.
Okay. And then, so for your attitude determination, what was the purpose of having two sensors? Was that for error accounting, or what was the point of that?
I'll defer to Abigail Kudum.
Again, this was a requirement that was based off of an objective that was defined by the customer. The customer specifically wanted two methods of attitude determination and control, so we provided two. Does that answer your question?
No, sure, yeah. Customer says, I do. On slide 90, I heard that you said that the requirement was to autonomously and manually accomplish that requirement, and you said you validated that, but I understand you guys didn't do anything autonomous. So was that just a slip of the tongue? Or?
Defer to Damien Barraza.
Yes, it was. I meant to say that it was autonomously simulated, or simulated in autonomous mode, but then experimentally tested manually.
Okay.
Sorry about that.
That was one of the suggested improvements that we had. One thing, looking at our system objectives, we had that tertiary objective to complete the system in autonomous mode, but we never had any requirements pertaining to that objective whatsoever. So if we could redesign specifically the GNC subsystem requirements, we would include, okay, GNC has to have this accuracy capability to conduct the mission in manual mode, and this probably tighter accuracy requirement to conduct the mission in autonomous mode. But we never had requirements for either mode. Does that make sense?
Sure, or time.
Yeah, time too.
Okay. So one of the other questions, last question, the main control modules and anything that isn't a motor, are those taking power from the 4 batteries, or how is that scheme implemented?
Kind of a brain left.
So it's a bit complicated. The microcontroller system is actually powered through 2 ESCs. So actually underneath the solar panel, I should have pulled them out, but I didn't because it's kind of a pain to pull them out. There's actually 2 printed circuit boards in there. The purpose of those boards is to regulate the 25 volts down to 12 volts for our ground motors, and also that would power our previous design, which was our solenoids. Now we changed from the solenoids to our microcontroller with the servos. And so for the microcontrollers, the nice thing was we had these electronic speed controllers which had what's called a battery eliminator circuit. And what that does is on the lines we have the control signal, the ground signal, and a power signal. And you can actually take up to 5 amps off of this power signal to power anything on a 5-volt line. So we use this power signal to power our microcontroller and all of our sensors on a 5-volt line. The microcontroller itself regulated from 5 volts down to 3.3 for any of the sensors.
Okay, great. And thank you very much.
Thank you.
All right, my name is Connor Warren. I think I forgot to introduce myself the last few times, and I do rocket propulsion in California. So I'll just start off by saying, good presentation, you guys. You guys covered a lot of ground clearly, both figuratively and literally. But with that, I do have a few comments. Slide 10. Can one of you define full autonomous mode for me?
Full autonomous mode means that we can plug in the target coordinates, and just by any of the allowable obstacles in the way, it should be able to get there as long as it's within the specified range.
Okay, so do you mean with absolutely no operator interference? Do you plug in coordinates that you want to go to? Okay. I just ask because this one has personally bitten me a lot. Because people always have a different idea of what autonomy means for some reason. It's just an example of how you got to be very careful and you got to pound your requirements very clearly at the beginning. Because otherwise someone will run with it and think that you're going to do much more than you actually want to do. Okay, slide 12. So I think you guys have answered this, but I just can't remember what you said. But was there a reason why you couldn't rotate or sense that the wall was 10 meters wide without having to translate the 10 meters to?
So the sensors that we have a range of 4 meters across. So in order to sense that far, you have to run along it.
Okay. Okay. Do they have, how much range do they have? Just out of curiosity.
It's about 4 meters.
Oh, so it's 4
Okay. 4 to 5 meters.
Okay. Okay. I guess that answers that question. It just seemed a little odd to me that you made that decision. Any other comments? I like this place, the display stand. I'd also like the compartmentalization you guys had in your presentation. It was pretty good. It's pretty succinct. Also like your use of blast shields, because as far as I can tell, you all still have your hands. Now that said, slide 91. I can't quite tell, but were the motors plugged into this?
No, they're not.
Okay. So this one kind of worried me because I couldn't tell. And when you got down right beside it, I'm just thinking, that road will cut you. It'll really mess you up. So it's just, I couldn't quite tell. But as long as you guys are following good safety procedures, that's good. thrust was already addressed. I don't really have that much. A lot of what I've said would just be repeating what I've said to other teams. So good job, you guys. It's good to see that you got to the subsystem tests, but when you've got to test a lot of subsystems, it gets hard to get to that final test. So hopefully you guys can test it during finals week, right?
Hi guys, I'm Jody Davis. I'm at NASA Langley. Just came from NASA Goddard, worked JWST hardware integration. So congratulations, that was a really good job. A lot of material in a short period of time. I really liked in your presentation how you had areas of improvement for each subsystem. I thought that was really good to call that out. And you guys were really thinking about that. I also liked the software used was called out specifically in your tables in some of the appropriate subsystems. That was helpful. Off-nominal scenarios, I've been picking up people with this. The operational aspect when you're in the air transportation mode, if you have a propeller out, that sort of scenario, did you guys think of any other contingencies, any other off-nominal scenarios that you have to test or think about or worry about?
Okay, I'll pass off to Christopher Klein.
Yeah, we thought about it. What we determined is we'd have to stop throttling the paired propeller, and then it would go out of control, and we would hopefully be able to come down slowly, firing the other two at max. We never implemented this in Simulink or anything because we didn't get around to it, but we did think about it. And that was kind of the idea.
Well, just thinking about it is a good step. Also, so I might have missed it, but were there any attitude rate requirements for the controller that I missed? Because we had attitude, but were there any rate requirements?
Pass off to Abigail Kudo.
No. So that was another thing. We learned a lot about designing requirements when we started to design and had nothing to design to. We took our subsystem requirements basically directly from the system level, and our subsystem requirements didn't tell us anything about how to design an actual controller. So when we went to sit down and do those simulations of the controller, well, how fast should we, adjust our attitude? We had none of these requirements defined because we didn't, I don't know. I think we designed our requirements not with design in mind, but only with the objectives that we had to satisfy in mind. So that was a huge takeaway that we got, especially in the Gnc subsystem, because the objectives given by the customer are not directly related to the kind of considerations you have to implement into such a complex system as an attitude determination or attitude control system.
My only comment with that is there's a ton of research out there. I also work in our science laboratory, and there's some really good GNC papers where they show the assessment to the requirements that even though you might not be able to get access to the requirements document, a lot of good papers out there address some of the gotchas and the requirements that they could kind of get an idea from other projects. Thank you.
Yeah, thank you.
On slide 111, maybe my memory was foggy, but was there a swap from aluminum to steel in that, and how did that affect the mass budget at all?
So this beam was just for the purpose of testing the thrust. Sorry. This is my test. I looked right at him. All right, so this beam was just for the purpose of testing our thrust, and we were using aluminum when this video was taken. It did cause permanent deformation, which is why we switched to steel for the later tests, including the one that gave the data shown on the next slide.
Okay, all right, cool, that clears that up, thanks. Yes. And then kind of the last question that I have is on slide 126. This is just kind of generally, where are the torque callouts for the bolted interfaces in your assembly drawings? Are they specified somewhere else in a procedure?
Pass off to never mind, William Hainsworth.
All the torques we performed were down to just a 2-finger tightness, so we didn't go anything past that. There was an instance where it was required for the axle to hub on the motor, the terrestrial motor, required us to use Loctite because the length of screw that allows us to connect the hub to the axle is only 2 millimeters of depth, and if you go any deeper than that, you go into the nylon washer on the hub and then it digs in. So it was necessary for us that we found due to driving over surfaces, it required us to put in Loctite, but everything else was just a 2-finger tightness to lock things in place.
So I would just recommend setting up, have a note and have that called out in the drawing. But that's really important, even though they're just finger tight. And then the other thing, the lessons learned, I'm glad that you had them. I would have just spent some time going through those because those are so important. I mean, even at NASA, they're coveted. Those lessons learned can propagate to the next project, so they're really important, but nice work.
I think I have just a minute, so I will say I would have liked to see a better job done with the cover for your protect your electronics, especially thinking about your operating environment. Your environment is going to have you going through things, so rocks. I mean, even in the cell when it landed, one of the sensors was damaged on the bottom because there was debris. It was a multi-billion-dollar mission. There was debris that popped up, and a rock hit a sensor and it was gone forever. So certainly, I would not ever approve that to fly without seeing covers for that, just to protect your electronics and protect even the wires from snagging on the motors. I can only imagine the mess that would be in flight. So it would be a spectacular YouTube video. So there's that. And then I would like to see some of the margins in your results as well. And then, did you guys think about using GPS sensors as for your autonomous driving?
In fact, we do actually have a GPS unit for the autonomous. That's what we were intending on using. Yeah.
Okay. And then, yes, I would have liked to see the lessons learned as well. I do want to point out that you guys did a very good job using that as a visual prop to point things out. That was really nice. Thank you for doing that. That helped contextualize and visualize what you guys were doing. And then my last comments are having to do with requirements. You guys a few times talked about how the customer gave you requirements. One of the hardest things to do in engineering is understanding requirements. And oftentimes you really have to probe the customer what is the rationale for their requirement. Because they might have written a requirement, give you an objective with an idea of what the final design looks like, and really constraining you. So you should have so in the future, ask for the rationale. Because really maybe that'll give you a way to negotiate with your customer. The other thing is requirement elaboration is really important. So just saying that my subsystem, I didn't have any high-level system requirements. Those are called self-derived requirements. So they're the things that you put in yourself in order to show that this is what I designed to and I met it, and even then go negotiate with your customer what those subsystem requirements are, even if they weren't derived from a high level. So self-derived requirements are perfectly fine. You want to limit those, but those are also a way to help you negotiate with your customer and make sure that they understand, hey, if you care, I think you should care about this, and this is what I think you should actually care about. So I think with that, I will say again, thank you and good job.